Okay, so issues and not results. There'll be a few results, but I think I'll focus on the issues for Palo Verde. First, a really brief overview of the kappa methods we're considering using. There's more where this Venn table comes from, and if you want the long version of all the methods to compute kappa, you can have a look at our paper. But the really brief reminder is this. So the traditional method I just used previously is what you do when you have relatively large large magnitudes. So you work above the corner frequency, and mainly kappa is the deviation you have from the assumed model. And that's the Anderson-Hoff method. And then if you have smallish events, then you go below the corner frequency. Okay, can I switch to the PDF because it's mangling some stuff? I didn't see that before. It ruined it in a pretty way, but still. Cheers. Okay, so yeah, this here is kind of a no-no. The omega square we're not sure about, but we're pretty sure that on the displacement source model there should be flat, so kappa is the deviation from that. That's the Piazzi-Smith method. So that's kappa ds for displacement spectrum or kappa mini. And whatever way you choose, then you have to just go back to zero distance and get your kappa not beneath your site. And then this method we haven't started applying, but it's the next step. So the kappa broadband is working both above and beneath the corner frequency. Just grab the whole spectrum, or as much as you have of it in this case, and just try to invert with reference to the point source stochastic model, and then you end up with a bunch of parameters, not just kappa. So you get your stress drop, you get your kappa, and you get a full frequency dependent model for Q. And there's a side amplification function in there too. A look at the data. So again, this is stolen from Jenny's presentation in workshop 1 in Oakland, and these are the 9 stations she showed they're going to get VS30 values for. The little star here is the Palo Verde site, and we have 1, 2, 3, 4 more stations from the TA array that recorded something. So yeah, the nearby and farthest away. This is plotting beautifully. These are the epicenters, so the biggest events are here, a 3.1 and a 3.4. Intermediate values, and these are actually 5. 1.5 is exactly at the same location, and the 1.2. And this is Palo Verde here. So this is maybe 50 kilometers, and that's maybe 200 kilometers there. Just a list of the events and the stations if anybody should need them. And again, I'll have to say that the data processing was done by Tadahiro Kishida at Peer. And it's, I think I have the reference there somewhere, so it's kind of a crash test on the data processing that, well, I think the peer review is, the peer report is still under review, so it's the documentation of the processing for that we're hoping to do for the entire NGA West 2 data set. So going for the from the time series, windowing, coda, S-waves, and what have you, and then getting Fourier spectra from them. So this is like the first time we're kind of trying to use data coming out of that process. This is an idea of the records you have. So from magnitude 1.2 up to 3.4, and now to maybe 300 kilometers. This is 50 kilometers right here, so you'll see there's, well, not a wealth of data for nearby events, unfortunately. And I'll start with the corner frequencies, because with smallish events, this is going to be an issue. So I started with I was suggested a typical stress value for Arizona, which is around 40 to 50 bars. So this is an idea of the corner frequencies you get. This is 70 here, so pretty high for the small events. We're interested because based on the corner frequency, we'll have to decide on the method as I showed before, so work above it or work beneath it. One other problem was we bumped into the Phillips paper that Gavin showed yesterday. And they use data from the same array, so from the TA. And most of their data plots here, so that's between 0.1 and 10 bars. So actually the center of the data for small magnitudes, so beneath 4 or 3, is around 1 bar. And that's kind of far from the 50 bars I assumed just previously. So we're just kind of trying and see where that'll bring us. So that'll make a hell of a difference for the corner frequency. And for the past year, I've been hearing people talking about trade-off between stress drop and corner frequency for small events. Well, now it really has my attention. This made my eyes bulge. So the reason I'm nagging about the corner frequency is that the sort of equipment that recorded these records is this. So this is your amplitude and phase for the broadband sensors. So they're pretty broadband for most purposes, but they're not really broadband enough for kappa. So they go up to 16 hertz, after which the Nyquist and the filter don't allow you to see pretty much anything. And then the lower bound of the data is kind of determined by these guys here, so by the least significant bits. And looking at the entirety of the data, I reckon that we should kind of disregard stuff that's like beneath 2 or 3 hertz. So what we're left with, oh no, this is just a by the way question. I'm not sure if the omega square model is what we should be comparing to, because sometimes the slopes seem to be like omega 3. Well, this one seems like to be, like it might be much steeper, and there's always like the possibility of high frequency amplification in there, so it's kind of a difficult question to tackle, but I want to put it out there that maybe it's not the typical omega square model. So this is basically what we end up with, so working between 4 and 16 hertz. This is just what's the word I'm looking for? This is just a stack of the noise spectra. So it's a pretty small bandwidth, and especially for kappa, and especially for small magnitudes. And this is kind of a combination of what we can see with our instrument and where all the possible corner frequencies are. So it kind of feels like we're wearing pretty narrow blinders here. And the best thing we can do is kind of based on the possible stress drops and the range of what the instrument allows us to see, we can choose our possible measurement methods, and that'll map onto uncertainty for the kappa estimation in the end. So we can either work beneath the corner frequency, above it, or use the broadband method to kind of try and extract all the source and path and side parameters. So hopefully we can try to wear the blinders in a bit of a more stylish fashion and move on. So if we start with method number 1, so the traditional kappa working above the corner frequency. So we're looking at these guys here, so above magnitude 3. Corner frequencies might range from here to here. Of course, they might range even outside, might be like even outside that range. Be that as it may, if we go kind of here, we can expect to maybe measure kappa as the deviation from the flat bit here on the acceleration model. And then if we focus on the baby earthquakes here, so 1.2 and lots of 1.5s, so lots of these guys, we can hope to go below the corner frequency where the displacement spectrum this time should be flat, and the deviation from that would be our kappa. And then we can use all the ample data we have to do the broadband kappa method. So I thought it would be useful to give you the knowledge I have or was able to get for site conditions, because it's pretty mixed up, kappa and site amplification, and I think the more we know about the site conditions at the site, the better. So the detailed description we got from the last workshop, this is copied from Jenny here. So there's only 3 sites for which there's like a sort of a description of the depth of the alluvia on top of the rock. So this is just an idea of the possible resonant frequencies we might have and whether they stand in the way of getting kappa or not. And then we have a map from the Arizona Geological Survey. You're not supposed to be able to make anything out of it. None of us did at the beginning. So these are contours for depth to base rock. This is Palo Verde here. And most of the stations that we're going to be using, they're either within the 1 or 200 meter contours. What I thought was a bit more interesting was that if you zoom in and you actually try to figure out what the colors correspond to, these are meters. So for example, here and here, I haven't checked the others, it seems like we have like relatively narrow basins that seem to be pretty deep, so down to maybe 3,000 meters. This distance is maybe 50 kilometers, so this distance is quite smaller than that. And I'm going to combine that with some more info. So I just dragged out a good old geopolitical map, just to give me an idea of what the landscape's there. This is probably well known to you, but as you know from the previous workshop, I'm known for plotting Arizona on top of what is apparently Texas. So now I think you'll be very proud of me for being able to tell you that where the green bit is, for example, Phoenix has an elevation of around 400 meters. Then if you look at Tucson, which is like the light brown shade, that'll be no more than 800 meters in elevation. And if you go to the north of this, to the Catalina Mountains, then you might go up to like 3,000 meters elevation. I learned a lot. So if we overlay these elements 2 and 3, we kind of see that these two really deep basins, they both plot within the low ground. So the elevation is no more than 3 or 4 or 500 meters. And yet they're mapped as having depths of maybe more than 3,000 meters, so I think that's something to look into eventually, because to me it shows like the underlying structure is kind of, well, complex. So I think that waves coming in and going through that sort of thing, that might add extra attenuation and it might map out in kappa somehow. So I just thought I'd draw your attention. And last, I tried to use the data available to get an idea for site conditions by computing H/V ratios. I did it for noise, S waves, and coda. I'm just going to show you the coda. So if you look at the entire frequency band, it can give us an idea of the amplification pattern, and we can get an idea of the site conditions. And then if we focus on the high frequency bit, it can kind of give us a clue as to whether we might expect some bias for the kappa computation, like if we have a downward or an upward trend that will inflate or deflate the kappa. And this is what I came out with. So stations that are kind of on the mountains, as expected, they'll give you like some high frequency side effects here. The window is between 4 and 16, so it's the window we're going to be working with. And these guys who are nearer to the plane, sometimes they'll either have like low frequency amplifications or just something more steady for the high frequencies. And finally, and I don't know in how long a time, we're going to have the full VS profiles from the measurements that Carola mentioned for these nice stations here. So if we do that, we can get the actual amplification and won't need to worry about the H/V as a proxy anymore. So going into the traditional kappa method results, we're just working with events 1 and 2 here, so 3 and 3.5. So everything is kind of 200 kilometers far from the Palo Verde site. So scenario 1 was a stress drop of around 1 bar, or let's say just a lowish stress drop following the Kevin's paper. So if we look at the spectra for the biggest event, we do see a kink here. The question is, what is this kink? Scenario 1 says it might be the corner frequency, so that's around 2 or 3 hertz. That means that above it we can measure kappa, and any sort of deviation from this line would be kappa acceleration spectrum. Scenario 2, which is the typical Arizona value of around 50 bars, that says that the corner frequency would be quite higher. So for us, that just means that we're going to use the same kappa method, but we'll have to push the higher frequencies and then not be left with too much of a bandwidth until our instrument fails us. It's hard to tell due to the amplification, but this is what I tried to do. So using the entire available frequency band and assuming a really small stress drop, we're just using as much as possible, and then pushing to the higher frequencies, assuming the bigger stress drop. It kind of gives a difference. So these are the results with distance for scenario 1. So you get like lower values and a bit of a negative here. And then if you push to the higher frequencies, it goes up. I'm kind of leaning towards the second interpretation. It kind of makes a bit more sense to me. Though I reckon we might as well use it kind of everything together and look at it as part of the uncertainty. But one alternative interpretation I think is kind of worth noticing is that we only have 2 data points here, but at 10 and 50 kilometers they have the same value. So I think it might be worth considering the hockey stick interpretation for the distance dependence. So Glenn Biazzi and Debbie Kilb have found that in their work. So that says that the deeper, I will just read Glenn's words. So very high Qs and the deep mid-crustal depth rays that rays concentrate in out to 30 to 50 kilometers. So this is Glenn's interpretation for sometimes keeping this hockey stick here and not extrapolating down to 0. And then this is just to say that the points I showed up to now are the results of stacking the horizontal components together for all events we have. So for each site, like these are all the sites that recorded something. For each site, I showed you 1 point before. In reality, the results can also look like this. So we have a big scatter if we don't stack them together. And if we want to consider the H over V's shown before, they're just a proxy, but for some of the data, they might kind of explain a few things. So again, there's no difference between green and brown even for me now, but these are green and these are brown. So it's kind of supposed to say that the sites that lie on mountainous areas and where you have this, I'll just show it, yeah, where the H over V just drops down like sharply in the frequency range we're using, then it might tend to kind of bring up your kappa. And then these 2 sites which float lower, maybe it's also correlated to the H over V kind of going uphill in that frequency range. But of course, there's much more to finally interpret in this. So a few prelim conclusions from the traditional kappa approach. So obviously there's big scatter, and I can't remember one single kappa work where I did not say that there is big scatter in the results. So there you have it, big scatter. The stacking between different components and events makes it a bit more robust. But still the kappas you get are a mixture of attenuation and amplification. So you can trust the kappas a bit more if the H over V is kind of flat, but that's just really a proxy. So after we get the VS profiles and get rid of the amplification, maybe we'll be able to get like truer kappas, like rock values of kappa. And after that, we can maybe have another look at first the AZGS contour map with like the really weird valleys plotted for the basement ceiling, and the elegant map that Kevin showed yesterday with the Q values. This is just a peek at that. So this time you are here, and this time I know this is not Texas. So I blew up the right portion of the map, and this is what the Q structure looks like for our region here. So this time it's pretty complex, so it'll go from 600 or maybe lower up to maybe 1200. And if we kind of get our kappas kind of more corrected, maybe we'll be able to trace differences in the different paths that they have followed. So this guy here, maybe we'll be able to see that indeed he went through a higher attenuation range, and this guy here, maybe we'll be able to see a final smaller kappa because he went through the easier path here. But that's something for the future. And finally, just a few results for the kappa mini method. I have no idea how much time I have left. Just tell me to start when I must stop. So these are the little events used for the kappa mini. So we're here in the south now. So mainly in the plane. Okay, the method I talked about. So scenario 1, tiny stress drop, tells us that the kink we see in the acceleration spectrum for the tiniest event might actually be an insanely low corner frequency. If that is the case, we could check the possibility of computing traditional kappa here rather than doing the mini method. And the Scenario 2, which gives us a stress drop of around 50 bars, would say that corner frequency should be somewhere out here, so between here and there, really. So the kink here must be kappa kicking in before the corner frequency and starting to chew up what should otherwise keep going out to the corner frequency, which is totally invisible to us. So I just went ahead with both scenarios and played along and saw what I got. So one case, we're plotting here for corner frequency. The other case would be kind of there. And let's see what happens. If I go with scenario 1, this is the high frequency bit of all the S-wave spectra. And again, it's stacked spectra, so both components and all the different events. So it's up to 12 stacked spectra here. And they all go uphill, so there ain't no way that all the sides show that sort of an amplification. So I think this means that in this case, we're before the corner frequency, and this is probably a more believable interpretation. So if we go for the second scenario, then indeed most of the spectra are going down. This guy is not, but this guy is just following exactly the 10 hertz resonance we saw on the H over V. So this is not very, very strange. And these are the results with distance. I'm just keeping the scale from previously, which went out to 300. Here we have nothing above 100 kilometers. And if we disregard this point, which I explained, then we kind of have a biggish scatter and no notion as to any sort of Q effect, so no notion of distance dependence. So just assuming that there is some sort of a slope here, but it's kind of lost within the dispersion, I just kind of stacked once again for similar distances and ended up with 3 points this time, and again it's kind of a constant value around 30 milliseconds. And finally, this is just an overlay of the two methods. So traditional method, kappas plot like this, so little circles, and the kappa minis plot as these x's. One thing to to point out, I guess, is that the kappa minis are systematically higher than the not very numerous, but still. They plot above here, and that's been seen before by Glenn Biazzi and John Anderson when they worked with Nevada data. And actually, they say that for the magnitude has to be really small in order for kappa mini to be at its best. So kappa mini is at its best when you're working with a magnitude 0.25, and we're working with like 1.5. So yeah, but we're still viewing the kappa mini as like the upper possible bound of the kappa. So in that we agree with those guys. So again, if you just go for a straight line, you're going to end up with quite a small 12-second kappa zero. The Q is rather high, but not extremely unreasonable with respect to the Q of Maeda and friends. Then if you go for the hockey stick, you go up to maybe around 20 milliseconds. The plus or minus is around 15 milliseconds in either case. And that's kind of it. This is kind of the result from everything we've done with all the doubts and questions we have. And then this is just what we're going to do, just do the broadband thing, and maybe that'll give an answer to whether the stress drop is really high, really low, or somewhere in between, which is a case I didn't really look into. So finally, and I'll be over in 1 minute, there's a bunch of problems. So we have small magnitudes, we have the infamous corner frequency stress drop trade-off, we have the now infamous to me TA array with a really tiny bandwidth we can see through, and we have a lot of high frequency side effects. So this is a fun thing to work on. And we have big stacker and big scatter, and we saw that the stacking can kind of help us work through it and give us something more robust. But at the end of the day, the question is still, where do you want kappa? Because if you want it at the surface, it's going to still be a mix of attenuation and amplification. And if you want to be able to get rid of the amplification correctly, then we can start working on that when we get the VS measurements. So we're going to have a VS profile maybe for a couple of some dozens of meters, and then we can kind of put that on top of the generic profiles, work out the cluster amplification, get it out of the way, and then be able to maybe look at the real kappas, and perhaps then it'll make more sense to compare both with the Mayeda data and with the AZGS data. And I think that's it. So maybe we can go ahead with a bit more style. And these are the references, and thanks for the chats with these guys here.
Thank you, Olga.